CAMs, ROMs, and PLA. So CAM is the content addressable memories, and that is like previously we provided address to read out the contents on that address, but in sometimes we want to provide the secret key to the memory, then finds the memory content that matches to that secret key. That is that kind of operation is widely used in like a CPU. So for example, if you want to find some key contents, we search the address, search the memory space, and that matches to the secret key, and then read out whole block around that that key match the element. So in another application is the network cards, where we send out the packet including the IP address in it. We want in the network switch receive that the packet, it need to find where need to send out that data to the desired port. There are multiple ports, so the network ATM need to decide which port we will send the data to. So in that case, it has the contents memory, the table where it store the target IP address and desire the port location, something like that. So that kind of operation require contents addressable memories. Another one is read-only memories, that even though the power is off, the memory content is stay there. We will keep doing the operation. Another one is the programmable logic arrays. So we can program the logic by software, so we can reconfigure the logic. So that is very widely used the application that you typically use Xilinx or the Altera. They provide such kind of a logic array. So CAM, so this is the extension of ordinary memory. So in the typical memory, we provide address and read-write operation that we look at the contents, but in this case we sometimes we provide the data onto the CAM and find the contents that match to the data. So which words had the same key or same contents in the memory space. So we select the contents and give out the memory location or some each So this is the typical 10T CAM cell. So CAM cell operation, we need to find something that comparison capability inside the cell. So we have a basic cross-coupled inverter and access transistor, but we have a different thing here. So match line here. If we, so let's say the contents inside here high and low, and then if we assert the high and low on the bit and bit bar, if the internal value, this is high and bit bar is, let's say, low, then the match field will stay high. So initially we match line, we pre-charge the match line to VDD. If the contents match to the value that we provide on the bit and bit bar, then match will stay high. If this doesn't match, if the bit and bit bar doesn't match to the internal value, then it will pull down path. One of the pull down paths will happen, so match line will go down. So this is typical the comparison block logic. So by having additional 4 transistor there, we can do the comparison with the data that provide onto the bit and bit bar. This is the typical CAM cell layout, very compact. We have a match line here, additional match line, right? This is overall block diagram of the CAM cell. We can show that how that operate as like in this sequence. First, we leave the word line all 0, so disable all the word line, and then first precharge the match line to VDD. Here, all the match line precharge to VDD, and then assert the key contents that on the bit line, right? And then wait for match line stage high. If the value on the bit line match to contents inside the SRAM, if those two are matched, and then pull down path inside the cell is disabled, and match line, one of the match line will stay high. So we can identify and locate where that matching entry presents here. Misline detection is like if all of the match signal goes to 0, then the miss will assert it, right? So there is this is basically NOR operation. So pseudo MOS NOR will be best for large number of input shown in here. So the output miss will go high if no words match here. Here, driven by the precharging here, this PMOS is used to precharge the match line, as I mentioned before. So read-only memory is another kind of memory cell, memory type. And this is non-volatile, meaning if you power off, the value stays inside the memory cell. So even though power is off, you can store the contents inside. So it retains their contents when power is removed. So the simple structure we can use is a mask programmed ROM. They use one transistor represent one bit. So if there is a transistor there, that we can either we can, depending on whether the transistor is connected or not, we can represent the 1 or 0. We will show that the structure in the following slides. So this is a ROM example. So this is a transistor. So we have a big pull up here. If there's a transistor presents, then it pulls down the bits. So if the word line, one of the word line address, if the address comes in, one of the word line asserted. Once they're asserted, then the transistor attached to it will be actively high on, so it will pull down the output. So this is like a pre-programmed value will be provided. So the existence of the transistor can be mapped like in this dot in this grid representation. Each dot will give us 1. So if this transistor presents, the output, this bit line will be driven to 0, and at the end, inverter will invert the value, so we will get the 1. So whenever the transistor presents, then we will get the logic 1. So basically, if you look at this structure there, it looks like we have a PMOS pseudo NMOS pull up and pull down. In the pull down path, we have a NFET. It looks like a pseudo NMOS NOR gate. So we have a word 0, 1, 2, 3. If there's a 1 present, we insert the transistor here, right? This is the hard-coded ROM. So once you design fabricate like this, you cannot change the value. Right? This is a non-volatile. That's why we cannot change it. We can the way we program is to placing the transistor there. This is an example of a ROM array. So this is one unit cell which has the NMOS transistor. So they're very compact structure there. This is only 1/10 size of SRAM because each single bit representation is done by transistor. Okay. This is the example of row decoder to assert the word line. This is so compact so that only single track per word presents. Right? This is the pitch match to the ROM structure. So each line, this is like word line. This is the complete ROM layout. This is the ROM array. This is a decoder, a row decoder. This is kind of a pre-decoder probably. As you can see, this is just an example of a ROM layout. The previous example was hard-coded ROM, but most of the case we want to program the ROM contents, read-only contents. Although that is read-only, sometimes we want to program that value to either 1 or 0 electrically. So this is typically widely used nowadays. So here is the example of the ROM, programmable ROM. We have a this structure transistor similar to NMOS, but it has a floating gate in between the gate and channel. So this floating gate has the kind of a practical the role of storing the value. So having this, if we assert the very high voltage on the gate, the channel, the electron on the channel will jump onto this floating gate, and that will change the threshold voltage of the transistor represented in here. So if the transistor threshold is nominal threshold is there, if somehow if we program by applying large voltage, then threshold will shift to higher voltage because there is more electron trapped on the floating gate. That actually require more voltage to make this actual channel inversion. This is called the electrically programmed ROM structure. This is ID versus VGS, for example. So we have two different state of transistor characteristic. If you remove that the charge trapped on the floating gate, we assert the gate voltage large negative voltage, then this negative charge will disappear. So in this way we can program the transistor threshold voltage. The ROM is quite largely applicable. We can use the programmable ROM as a logic array. So combination logic can be implemented with the ROM structure. So address behaves like input and output comes out of the array and the memory. So if we provide a certain value on the input that looks like array, so the address in each address will have some contents there depending on the logic, combination logic, the function, that value, the output will come out. So this can be used as a finite inside the finite state machine. So this kind of a ROM structure replace the combination logic. So we have a flip-flop here, so we can easily implement the finite state machine. This is so I'm not sure you guys learned about finite state machine in the digital logic design. So we know that there are two kinds of the state machine. One is Moore machine and Milli machine. You need to distinguish those two. So if you use ROM as a lookup tables, for example, we have n input and k bit outputs. Require how many memory space? 2 to the power of n words with each k bit entry. So n address space give us 2 to the power of n words. So changing function can be done by reprogramming the ROM contents. So for finite state machine implementation, so we need additional extra input from the state input. So n input, so memory ROM address space need to be larger. So n plus s bit is required for the ROM address. The content will be, output will be k plus s bit registers, right? This is something that you can consider for ROM implementation as a finite state machine. So this is the example of the finite state machine implementation using RoboAnt. The little robot, ant robot, it has a sensor on the left and right. Whenever this sensor hit with the wall, it will indicate 1. So L and R is a sensor antenna. So when in contact with the wall, it will assert T1. The actuator is leg, so the leg will move forward or turn left or turn right. This is function that we can give us for the output. Our goal is to get out of this maze. So starting from right down up lower corner, it finds out find the way out. So the strategy is to keep antenna, left and right antenna on the wall to keep track the valid space. Okay. First action is that we will go forward until we hit the wall. So we're starting from the lowest state. If nothing happen on the left and right sensor, then we keep inside the lowest state, and that action is forward. Keep forward. We will keep going forward. If one of the L or R is hit, so we hit the wall, left or right, then we go to the next state. So we go to the RCCW state. So in this example, if the left and right, the sensor will only hit the left or both or right. On those three inputs, we will switch to a different stage. First, we will turn left whenever left or right only single sensor is hit. Then we will stay in this state and we do the turn left. Always we turn left, and then none of these contact happen, L or R happen, then we turn left and then transition to new state. Now we go to wall first state, and if the left or right, so right is hit and or right is not hit, we change is in this wall one state we keep turn right and forward. So turn right and forward is kind of combination, so you will switch it back and forth between two output probably. So and move forward, so turn left and forward and turn right forward, so we going back in two state. This kind of algorithm you will make a new algorithm depending on how you perform in actual setup experiment. Let's go forward. So you can continue and finish. You can, once you draw the state machine transition, you can optimize the transition like this. Final, we have a 1, 2, 3, 4 state, and between the state we have a condition and also outputs, right? Showing each state will give us the certain output. This is the final state transition table. In each state, depending on the input, will generate the output. Right? We have a 1, 2, 3, 4 state. Each 4 state we look at the left and right input control, and the next state, depending on the input, the next state is defined, and also the output, right? Are defined. Output is 3 signal: turn right, turn left, and forward. Right? We have a turn left and forward, right? We have a turning left and going forward at the same time, shown in here. That can be kind of keep moving. In this way, we can move the RoboAnt key forward. Right? So once we finish the state machine, we fill in the state machine contents. We have a 4 address composed of 2 current states and 2 inputs from the sensor. So 2 sensor input comes in, and the current state comes in, the new state, and output, turn left and turn right, forward signal will be mapped. So from the previous table, we fill in the entry, the logic value by hand. Finally, we'll get this programmed onto ROM that will give us RoboAnt operation. PLA is the programmable logic array. It can perform any function in some of the product form. So some of the product form is like this format. So each product is summed like that. This is OR operation, and this is the AND operation inside, right? So any logic can be represented in this kind of a sum of the products form. And then first we have to implement the AND operation, and then lastly we implement the OR operation here. So depending on the input logic that you wanna implement, you define the connection of the input and input bar available in here. You define the connection here like this. Then you can make any logic you can imagine using this PLA structure. This is an array structure that already present for AND and OR and input inversion like this. So if you have many of them, then you can actually implement any logic function you want. So as you can see, the AND and OR logics are not very efficient by itself. So we may use the pseudo-MOS dynamics logic style or pseudo-MOS style to leverage its performance. So we can simplify the logic design, and we can make it very compact and put as many logic as possible inside. So we know that by bubble pushing technique, we are using the De Morgan's law to convert all the logic to all NOR gate. Here this is NOR, this is also NOR. So NOR is very good for handling the many input logic, right, by having pseudo-MOS style. So this is kind of a NOR style PLA to implement the more dense structures. So for PLA schematic and layout example shown in here, in PLA you can enable this kind of transistor here. We have an end plane. So this is a pseudo ratio logic there. We have a PMOS pull up is always on, weakly on. Depending on the pull down, we enable pull down, one of the pull down. This is the ratio logic, right? Grounded, and many multiple MOS on the pull down, right? Structures. So use that here in the end plane, and also OR plane, the same thing. So this is the NOR PLA schematic example, and each layout is also very compact as shown in here. So as you can see, the OR plane, the PLA is very similar to ROM array. The ROM array had the single transistor to program the contents. The PLA is also a single transistor to do the logic function, especially when you use the ratioed logic, ratioed NOR, the logic gate there. So end plane of the PLA is like a ROM decoder and ROM. So those PLA and ROMs are looks like very similar, but PLAs are more flexible than ROM because of the following reason. The PLA has less number of rows for n inputs. PLA need to just generate the min term that are needed, right? The term that we have to complete. And also we can use the logic simplification to take advantage of it. So PLA can be more compactly designed rather compared to ROM. This is an example of RoboAnt using PLA. In the previous example, we had the input of a state, current state, and left and right, and then output of the next state, and turn right and turn left and forward output. In this case, we have to decode the input, 4 input. We have to decode the 4 input, but by having the logic optimization, we can minimize the number of the terms, right? Like this. And also, as the 0 bar can be also optimized using very small number of inputs. So having this kind of optimized representation by logic reduction, so we can have the another turn right and turn left and turn key forward can be optimized to represent the number of minimize the min term number of the term here shown in here, right? So what we need to implement the PLA is just implement this kind of simplified form. But in the ROM implementation, we have to specify all the inputs, right? But in PLA, we can use less number of min term shown here. Finally, this is the end plane and OR plane. So in end plane, we implement this each term, and the OR plane we take all these OR. So this is the final implementation with the 4 inputs and 5 outputs. So number of row and the terms and the line in each here, we just implement each min term, right? On this, how many min term cases? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 cases. The min terms are only implemented in this dot diagram. Okay, this can be simpler than actual ROM implementation.